All right, section 5.1.1, we're looking at solving equations algebraically, talking about linear first, then quadratic, and also radical equations. There are two strategies we're going to use here to solve equations algebraically. One's called undoing, which is what you're used to with just using opposite operations, and another one called rewriting. If there's a more convenient way to see the equation, we'll rewrite it into a different format. So first with undoing. The undoing strategy is when we're performing operations backwards. So adding becomes subtraction, multiplication becomes division, and so forth. So we write it like this inverse. Remember to undo each step, although we never called it undoing before we solved linear equations by undoing and rewriting. So all of these equations that you see here, you're used to having done opposite operations to solve them, but let's talk through each one. So example 1, subtracting 3x gives us 4x, subtracting 2 gives us 92, and then dividing 4 is the opposite of multiplying 4, and so we get our result. So that was strictly undoing. In example 2, we can use rewriting first by using the distributive property. So another way to write this first part here is to distribute the 7.5, and also then we need to combine our like terms. And at the same time that I combined 7.5x and 4x, I also subtracted the 31.5 to the right side. So this was a combination of rewriting and undoing on this line. And then finally undoing the division, with division, undoing multiplication to get our result. Example 3, we have a scenario where we can undo first, right? So if we undo with plus 3, we end up with 10. And then also undoing the fraction. So the reciprocal of the fraction is 2/5. Multiplying 10 by 2/5 gives us 4. So linear equations all came with combinations. For these next three, if you want to pause the video and try them, and then we'll come back and you can take a look at how you did. All right, for number 1, if we use a combination of undoing, actually this one's pretty much only undoing, we should get x equals 8. Number 2 required rewriting and undoing, and in the end, w equals 3. And for number 3, it was also rewriting and undoing, and we got x equals 18. Now, if any of those were different than what you had, first look through the steps and see if you can find your mistake, but if not, make a note of it, and we'll talk about it in class. All right, so we can use this undoing strategy for quadratics as well if there's a single x squared in the equation and no plain x. So the way I'm undoing the quadratic in example 4 is I'm working with the reverse of the order of operations. So order of operations would tell me to add 3 first and then square and then multiply and then subtract. So I'm doing it in reverse order. Getting rid of the minus 5 first by adding 5, that gives me 27. Dividing the 3 gives me 9. If I have a binomial squared, I can isolate it by square rooting, and the square root of 9 is plus and minus 3 when solving an equation. And then subtracting 3 gets x by itself. So I have the minus 3 from subtracting it, and then the plus and minus 3 from the square root part. So if I take negative 3 plus 3, I get 0. And if I take negative 3 minus 3, I get negative 6. So there's two answers to this, just like there would be in any quadratic, or most quadratics. So undoing will get us there. Example 5, same kind of thing. I'm subtracting 6 first to get 18, dividing by 2 to get 9. Again, it's plus and minus 3, and when I add the 2, I have 2 plus and minus 3. So 2 plus 3 is 5, 2 minus 3 is negative 1. Just remember when you square root, that square goes away, and so we're no longer dealing with any kind of exponent on the left side. All right, so on to the next page, page 7, top of the page. Give this one a try on pause, and then come back and check it out. All right, so the first thing we want to do with this is add the 2, and then we're going to divide the 5. When we square root, we get plus and minus 4, and the square goes away. So if I add 5, I get positive 5 plus and minus 4. You should have had 9 and 1. Okay, so radical equations work the same way. We're trying to isolate the radical first and then square. So in example 6, to isolate the radical, I had to divide by 3. That gave me 5. And then to lose the radical, to get rid of the radical, I had to square. So squaring the radical makes that go away, and I just have the radicand. And squaring the 5 becomes 25. There's no plus and minus when you go this way. Plus and minus occurs when you do a square root, but when you get rid of a square root, you're not going to have a plus or minus, you're just going to square the number. Adding 1 gives me 26, and dividing 2 gives me 13. You can always go back and check your work. Example 7, same thing. I'm adding 3 this time, so trying to isolate the radical again. Adding 3 first, dividing 7 next, squaring, and then subtracting 1. I have my result. All right, and then you can give this one a try in the middle of the page. And so we're subtracting 4 first, we're dividing 2, we're squaring, and we're adding 7. So these should be hopefully fairly basic for you. All right, it's always a good idea to check your solutions. To check your solution, you're just going to substitute your answers in for x in the original equation. If the statement's true, you're good. If it's false, then it's incorrect. So for example 4, if we went back and inserted our answers, it does check out for both of them. When we put in a 0, it works out that both sides are the same. And when we put in a -6, it works out that both sides are the same. So to solve algebraically a number 8, this was a little bit different because there is a square root. So to isolate that part, I have to square. But when I square, to get rid of the square root, I'm creating an x squared on the left. So this turns into a quadratic equation. Right? There was no squaring in the original problem, but now it becomes quadratic. So subtracting the 2x and subtracting the 3 gives me this trinomial. So remember, anytime I try to solve a quadratic with an x squared and an x, I have to move everything to one side. So once it's here, then I can factor it, x minus 3x plus 1. And so solving it gives me x equals 3 and x equals -1. However, when I go to check this, you're going to see that one of those answers doesn't work. So if I put in a 3 for x, I have a 3 on the left, I have a 3 underneath the root with the 2. This is 6 plus 3, which is 9, and square root of 9 is in fact 3. So that's fine. But when I put in -1, I have 2 times -1 plus 3, which is 1, and the square root of 1 is not -1. So that doesn't work. And that means that that -1 is what's called an extraneous solution. So whenever we're squaring to solve, if we're squaring a variable, usually we're going to end up with an extra solution that we don't need. Not always, but that's why we have to check. So the only actual answer to this problem was x equals 3. All right, page 8. When we use the rewriting strategy, we're writing the equation in equivalent format. And so to solve this quadratic from the previous page by using rewriting, instead of adding 5 and doing a square root, we have to write the binomial twice, multiply it out, combine our terms, move everything to one side, and factor to solve. So the process isn't hard, but it's longer. So I would suggest that if you have a binomial isolated, you just use the previous method. But if you have a problem that has x squared and an x, then you don't have that luxury. So I could not isolate this equation and do a square root because I'd have an x on the other side. So what I want to do here is multiply out the binomials, combine my terms, and bring everything from the right side over to the left as well, and then factor, and then solve. The same thing happens in example 2. I had to distribute on this part, and I had to multiply x plus 3 times itself. Just remember that when we have a square on a binomial, you must write it twice and multiply it. And then everything gets combined and moved, and we can factor the final result. So backing up to this previous one, in example 1, I only had a single instance of x in that squaring. So I was able to isolate it and solve it on the previous page. And I recommend that. But if you have multiple x's, one inside a square and one outside, you really don't have a choice. You must rewrite it and resolve it. Okay, example 3 has a coefficient in front, -1. So I square the x minus 5 first, then bring the -1 into that trinomial. This minus 25 and plus 17 and plus 7 would combine to give me minus 18. So if I add 18 to the right side, I get plus 8. And the reason why I'm moving these to the right side this time, I don't like to factor with a negative x squared. So if I have a negative x squared on the left, I'm going to move it over to the right instead, and then factor from there. And then finally, you can see in example 4 how that one works with a coefficient of 2. So just pause that and make sure you have that written down.